Alright, so for example number 6, let's find a power series representation for f of x equals arctan of x. And then find the interval of convergence. So this is a good example in which we will find a power series for, well, start as a starting point, the power series for the geometric series. Recall that the interval of convergence goes from -1 to 1 exclusive on the endpoint. But things are going to change when we do the operation related to get the power series for arctan x. Alright, so of course let's start with 1 over 1 minus x, which is 1 plus x squared plus x cubed plus dot dot dot, which equals sigma n equals 0 to infinity of x to the n. So that's the root, pretty much the root of all evil, if you will. And then from here we're going to deduct a new power series. Well, so I mean, how can we relate 1 over 1 minus x with arctangent x? Well, you can think of what we have done before, pretty much at the beginning of the semester, a way to obtain arctan x. Well, so which operation gives us an arctangent as a result? The derivative of one function? Well, we actually did the derivative of this function, and no, it doesn't give us an arctan. We got something else. Even the integral of this function, well, gave us something different, an ln. However, okay, so this one I'm just going to give it away because, well, I mean, it's not that obvious. So I'm going to start with 1 over 1 plus x squared, because if we integrate 1 over 1 plus x squared, the answer is arctangent of x. And well, in this case, this is the same as saying, well, keeping the idea that we want to obtain 1 minus negative x squared. All right, having that form. And then this will be sigma n equals 0 to infinity of negative x squared to the n. And well, let's actually simplify this series. That's going to be sigma n equals 0 to infinity of -1 to the n, x to the 2n, which is 2n. All right. And well, of course, you might want to expand a few terms over here. So notice this is going to be an alternating series starting with a positive. Well, for n equals to 0, -1 to the n, that's a positive of 1, and then x to the 2 times n, which in this case is 0, that's x to the 0, which is, well, that's just 1, minus x squared plus x to the 4th minus x to the 6th plus etc. This one is going to go on forever. And of course, number 1, let me focus on this series right here to find the interval of convergence for this series. And the interval of convergence for that series would come from, actually, from here, you know? The u, that is absolute value of u less than 1, where our u is negative x squared less than 1, which is, in this case, we'll find the absolute value of negative x squared. Well, that's going to give us x squared less than 1, and, well, absolute value of x, because if we take the square root of x squared for all real numbers is the absolute value of x, because x can be anything. And then from here, less than 1 and greater than -1, by the definition of those absolute value inequalities. All right, so let's see. That means that the potential, radius or interval of convergence is -1 to +1 exclusive. However, well, we're going to use this instead to find number 1 the series for arctangent, and then we're going to use this idea to find the actual, the actual interval of convergence, and you will see how things are going to change here. Okay, so let me take a few steps back. So 1 over 1 plus x squared equals, I'm going to go with this sigma right here. Sigma n equals 0 to infinity of -1 to the n, x to the 2n. And well, we're going to integrate both sides over here. So integrate with respect x, integrate with respect x. So when we do that, well, so the integral of 1 over 1 plus x squared, we know that's arctangent, and there we go. We're going to have a power series for arctangent x. This one is going to be sigma n equals 0 to infinity, and that's well, -1 to the n, and well, that's x to the 2n plus 1 over 2n plus 1. And well, I'm going to need some space over here. Let me move this real quick, and I need this for the plus c. All right, so we have a power series for arctangent. So that's our power series. Now, notice the similarity with a series that you have seen before. Yes, it's the one for sine. I believe it's the one for sine, but without the factorial. All right. So, well, so what is it? What we are going to verify whether this is indeed the interval of convergence or not. So from this series that I just obtained, we're going to test the endpoints. And in this case, well, I'm going to test x equals to -1. So that's going to be sigma n equals 0 to infinity. And that's n equals 0 to infinity of -1 to the n. Notice I don't need to write the c, that's fine. So that's going to be -1 to the 2n plus 1 over 2n plus 1. Alright, so what's going to happen here? So just be careful with the number of operations that we will do here. So number one, I'm going to write this sigma n equals 0 to infinity. So that's -1 to the n, this -1 to the 2n, -1 to the first. Using laws of exponents, the whole thing divided by 2n plus 1. Now, notice in this case, number one, notice this -1 to the 2n. Here in this case, we're always raising a -1 to an even number, regardless of what n is. So that will always be 1. And then when we put together -1 to the n, -1 to the first, this will be sigma n equals 0 to infinity. That's a -1 to the n plus 1 times 1 over 2n plus 1. So that's the series we will deal with. Alright, so in this case, let me make this look a little bit better. Alright, so now that we get this series, we need to find a suitable test to determine whether the series converges or diverges. And in this case, well, it looks like the alternating series test is a good candidate in this case. So let's go ahead and write down the first condition, that the limit 1 over 2n plus 1 n approaches infinity. Well, this is 0. Well, that meets the first condition. Alright, and well, now we need to determine whether the sequence is non-increasing, that is 1 over 2 times n plus 1 plus 1. Is that less than or equal 1 over 2n plus 1? Well, in this case, this is true because this n plus 1 shifting here will indeed give a denominator larger than on the right hand side of the inequality, making this indeed an inequality true. So this means that in this case converges. So what's going to happen for the radius of convergence here? Oh, for this one right here, it will be inclusive for the lower endpoint. See how it changes in accordance with the theorem that we looked in the previous video? All right. So let's see, let's test x equals to 1, and when we test x equals to 1, what are we gonna have? So sigma n equals 0 to infinity, -1 times 1 to the 2n plus 1 over 2n plus 1. That is, we're replacing x with 1 right here. And well, 1 to the 2n plus 1. Well, notice this is not alternating. So we are raising the number 1 to odd powers. That's always going to be 1. That's going to leave us with sigma n equals 0 to infinity of -1 to the n times 1 over 2n plus 1. And in this case, well, if you observe this series, we can pretty much do the same test as we did before. So use the same test result as before. All right, and of course this one will converge. So that means that at the upper endpoint 1, it's going to be inclusive, so this confirms this part of the theorem here. So let me go back to that part of the theorem. So it may, where it says here, so let me highlight it again. Let me highlight that part actually. It may happen that the original series converge at an endpoint, whereas the differentiated series or integrated series, in this case I should have be more specific about it. Well, it also it could diverge or converge or vice versa. All right, so this confirms this part of the theorem. All right, so let's look at another example, and well, in this case we're going to go back to Taylor and Maclaurin series. However, I mean, it's going to be the same process as we did before, but in this case, well, we're going to talk about this in more like a series, instead of as opposed to just a polynomial. So in this case, well, so let's find the Taylor series expansion for f of x equals e to the 4x at a equals to 2, and then find the interval of convergence. All right, so let's see. So number 1, so f of x, so as usual, we're going to take a few derivatives. Maybe, I think I'm going to take just 3 derivatives, that's enough. So f of x equals e to the 4x, and then evaluate this at 2, not at 0 but at 2, equals that's e to the 4 times 2, which is e to the 8. Take the derivative f prime, that's 4 e to the 4x, and f prime evaluated at 2 is 4 e to the 4 times 2, which again, that's in this case going to be 4 e to the 8. F double prime of x equals 4 times 4, which is 16, e to the 4x, f double prime of 2, that's 16 e to the 4 times 2, which is 16 e to the 8. And then the next term, so just a third derivative, 16 times 4, which is 64 e to the 4x, f triple prime, 16 times 4, that's 64 e to the 8, equals, in this case, 64, no, we should have done this intermediate step, 4 times 2, 64 e to the 8. Alright, so in this case, well, let's use the Taylor formula. Alright, let's use that Taylor formula. So in this case, let's see, so e to the 4x it's approximately, well, or rather equal. Let's use the equal sign. So that's f evaluated at 2 over 0 factorial plus f prime evaluated at 2 over 1 factorial times x minus 2, that's the center, plus f double prime evaluated at 2 over 2 factorial times x minus 2 squared plus f triple prime evaluated at 2 over 3 factorial times x minus 2 cubed plus dot dot dot. That one is going to go on forever, right? So f of 2, as we did in the previous section, and actually it was 11.1 at the previous one, f of 2 is e to the 8th. So that's e to the 8th over 0 factorial. Well, let's just leave it as a 0 factorial, which is 1. So f prime, which is 4 e to the 8th over 1 factorial times x minus 2 plus f double prime, which is 16 e to the 8th over 2 factorial. Let me leave it as a 2 factorial. I know this is in this case very tempting to evaluate the factorial, but let me leave everything in terms of factorials. And that's because we will be in the need of coming up with a general rule in terms of sigma notation, and if we do this simplification, we may not be able to accomplish such a task. Alright, so x minus 2 to the second plus the third derivative, which is 64 e to the 8th and over 3 factorial x minus 2 cubed plus dot dot dot. Alright, so let's find a way to come up with an expression in terms of sigma. So e to the 4x centered at a equals to 2. Well, it will be, of course, let's start with sigma n equals 0 to infinity. All right, and in this case, notice we have e to the 8th. Number 1, e to the 8th. The e to the 8th appears in all terms. And also notice how powers of 4 in this case, like 4, 16, 64, and well, there is an invisible power of 4, you know. So if you want to rewrite this, for example, that's 4 to the first power, that's 4 squared, this 16, that's 4 cubed, which is a 64, and this is basically an invisible one, which is 4 to the 0, if you will. Now, so let's express that as a 4 to the n power, and then notice how the sequence of factorials appears in the denominator. That's an n factorial x minus 2 to the n power, right? Which power n coincides with the factorial n. See 1 factorial to the first, 2 factorial, second power of x minus 2, factorial, power 3, etc. So that's the series representation of e to the 4x centered at 2. But they're asking us to find the interval of convergence, so of course we need to, okay, let's start with the series again. Can we use a different color here for the interval of convergence? So for the interval of convergence, okay, let's start with the series again. N equals 0 to infinity, e to the 8th, 4 to the n, x minus 2 to the n over n factorial. Recall in this case that we need to use the limit to set up as using the ratio test rather, n approaches infinity. And that's going to be the absolute value of a sub n plus 1 over a sub n. So this is limit as n approaches infinity. Okay, so it's going to be e to the 8th 4 to the n plus 1 x minus 2 to the n plus 1 divided by n plus 1 factorial times n factorial, that is the reciprocal of this again, as we did before, as we did a few times when we applied the ratio test. Let's just do that. E to the 8th 4 to the n x minus 2 to the n. And well, so number one, let's do a few simplifications. Notice how this e to the 8ths can cancel, and also we can, okay, let's rewrite this x minus 2 to the n plus 1 as x minus 2 to the n times x minus 2, and this 4 to the n plus 1 as 4 to the n times 4 to the n times 4. And then I'm going to simplify this factorial right here, and my n plus 1 factorial, and make it match with the n factorial. So that's a limit n approaches infinity, 4 to the n times 4 x minus 2 to the n x minus 2 to the first power, and that's n plus 1 times n factorial times n factorial over 4 to the n times x minus 2 to the n. Alright, and let's now actually divide out factors. 4 to the n, 4 to the n factorial with n factorial, and we're going to be left, also x minus 2 to the n, x minus 2 to the n. And this will leave us with the following. Change color here. This will leave us with, well, let me take this 4 outside of the limit, and approaches infinity, and I'm going to be left with this x minus 2 over n plus 1. But recall that this limit is in terms of n, not in terms of x. So everything in terms of x, I will also have it outside. Well, and this is 4 times the absolute value of x minus 2, limit n approaches infinity of 1 over n plus 1. And this limit happens to be 0, 4 times the absolute value of x minus 2, and that times 0. And while this limit is 0, and recall, so from the previous section, that when you find the radius of convergence, when the limit is 0, the radius is infinity. That means this series right here converges for all x, for the entire real number line. Alright, and well, if you think about the exponential function is a continuous function. It's continuous everywhere, doesn't have any vertical asymptotes, any holes, or any jump discontinuities. You know, so and if you recall, well, the interval of convergence, in a way, it's an interval. It's another way to find the domain of a function, but in this case, the interval of convergence coincides with the domain of the function that it represents. Now, if you think about all this that we did in one problem, it takes forever to do. I mean, finding 3, 4 derivatives, write down the Taylor series, figure out a way to express this in sigma notation, which may be tricky at some times. I agree with that. And then on top of that, having to go through the limit process of finding the radius of convergence. So there has to be like a shorter way to do it. And in fact, there is. But this, we will see it in the next video.